Hey everyone, welcome to today's Explainer. You know, if you've been studying physics for a while, you probably realize it's absolutely full of surprises. But today we're going to unlock something truly phenomenal. We're looking at an actual mathematical cheat code that nature has been using for literally millions of years to see in the dark. I know, it sounds a bit like magic, but I promise you, it's just pure, elegant physics. So get comfortable and let's dive right into this.
Okay, picture this. It's a completely moonless night, pitch black. You couldn't see your own hand in front of your face if you tried. Yet darting through the sky right above you is a bat, perfectly tracking and catching a tiny mosquito mid-flight. Like, how is that even possible? How does a bat catch this totally unpredictable little insect in the dark without just smacking into a tree? Well, the secret isn't in their eyes at all. It's actually in the air around them. It's all about invisible waves.
To wrap our heads around how these invisible waves actually work, just think about bouncing a basketball off a solid concrete wall. You throw the ball, it hits that flat surface, and boom, it bounces right back to you. Well, sound behaves exactly the same way. A huge property of all waves is that they can reflect. When a sound wave travels toward a large, smooth surface, it hits it and comes bouncing right back. Honestly, the only real difference between your basketball and that sound wave is that the sound wave isn't dragged down by gravity. It just travels straight.
So, putting on our physics hats for a second, an echo is simply the reflection of a sound wave. Imagine standing dead center in a totally empty room between two flat walls and just clapping your hands loudly. You're sending a sound wave traveling outward in every direction. And when that wave hits the hard, flat glass of a window or smooth concrete, it bounces perfectly back to your ears. You'll actually hear what sounds like a slightly delayed, longer version of your clap that kind of fades away. That weird acoustic effect? Yeah, that's an echo in action. And here's the crazy part. This super simple concept scales up to solve massive problems. Believe it or not, a bat hunting insects in the night sky and a giant ship hunting for deep water in the ocean are using the exact same physics principle. It's called acoustic ranging. The bat makes a high-pitched squeak, it bounces off the bug and echoes right back. Meanwhile, the boat sends a loud sound down to the ocean floor, it hits solid ground and bounces all the way back up to the ship. By just measuring that echo, both the animal and the machine can perfectly map out their unseen surroundings.
Okay, so how do they actually know the exact distance? Well, here is your ultimate detective tool, the secret formula for calculating distance using sound. It's just 3 steps. Step 1, measure the time. How long does it take for the echo to return? Step 2, multiply that time by the speed of sound for whatever medium you're in, like air or water. And step 3, divide by 2. Seriously, just memorize these 3 steps, measure, multiply, divide, and you'll be able to solve pretty much any acoustic ranging puzzle in the world.
Actually, let's pause right here for a second, because this next part is absolutely huge. Divide by 2. This is the ultimate gotcha step in physics. The #1 mistake students make is completely forgetting this final calculation. Why do we have to divide by 2? Well, because the total time you measured back in step 1, that was for a round trip. The sound wave had to travel all the way from the boat to the ocean floor and all the way back up to the boat. If you don't chop that number in half, you're literally calculating double the actual distance. We only want a one-way ticket here to find our target.
All right, you ready? Let's put your new superpower to the test. Let's look at a real-world scenario to see how this all comes together. Imagine you're the captain of a fishing boat, and you're using echolocation to find a massive school of fish swimming somewhere deep beneath you. You send a sound pulse pinging down into the water, and you hear the echo return exactly 0.2 seconds later. So, knowing the physics rules we literally just covered, can you find the fish? Let's break down the math together.
Okay, let's walk through it. First off, our medium is water, right? And the speed of sound in water is a blazingly fast 1,500 meters per second. Next, we have our measured echo time, which is 0.2 seconds. Now for step 2, we just multiply speed by time. So 1,500 times 0.2 gives us a total distance traveled of 300 meters. But hold on, do not forget our gotcha rule, that 300 meters is the whole round trip. So for step 3, we divide 300 by 2, which proves the fish are exactly 150 meters directly beneath our boat. Guys, you just use an invisible wave to mathematically pinpoint a hidden object in the dark. How incredibly cool is that?
Now, while bats and ship captains obviously love a good useful echo, not all reflections are actually helpful. Sure, we absolutely rely on this exact same bouncing wave principle for medical wonders like ultrasound imaging, which safely bounces sound waves inside a mother's body to create those amazing pictures of an unborn baby. But what happens when you really don't want the sound to bounce? Unwanted echoes are a massive headache for recording artists who are just trying to lay down a clean vocal track in a music studio. And if you've ever sat in a badly designed theater, you know that echoes bouncing all over the walls will clash with the original sound, making the actors' voices sound completely muddy and impossible to understand.
So, to combat this, architects essentially have to wage war against flat surfaces. They stick these bizarre geometric foam shapes all over recording studio walls, and they design super complex, weirdly angled ceilings in theaters. Because we know for a fact that sound reflects perfectly off large, smooth, flat surfaces like concrete and glass, engineers deliberately have to use soft, thick materials and weird, jagged shapes to trap those sound waves and stop them from bouncing back. They are quite literally destroying the echo on purpose.
Which brings me to one final, very practical question for you to chew on today. Knowing everything you now know about the secret math of echoes, if sound bounces flawlessly off hard, flat surfaces, how exactly would you keep your own secrets from echoing down the hall? Like if you were redesigning your bedroom right now, would you choose flat wood sheets, shiny metal, large mirrors, or maybe soft, thick curtains? Next time you walk into a room, I really want you to think about the physics of the spaces around you. Thanks so much for joining this explainer. Keep asking those great questions, and we'll catch you next time.